So 4.1, this is the beginning of Unit 4. And the first thing you need to learn from this unit is electronic configuration. Remember, I've always taken this example that you guys might be in a home, four of you, six of you, and in that specific home, each person has a specific room. So we can find a probability of meeting you in your room at a certain time. And so do electrons. So if in an atom you have 18 or 20 electrons, these electrons have specific locations where the probability of finding them is highest. And so in order to give these electrons an address, it results to what we call electronic configuration. So what are periods? In order for us to be able to draw the electronic configuration, we need to understand what periods are. So remember, on your periodic table, there are numbers to the left of your periodic table. It starts from 1 all the way to 7. Those numbers are called periods. So the horizontal arrangement of elements on the periodic table are called periods. As you can see, those boxes highlighted, they signify the period number. So the green one here signifies period 4. So on the periodic table, we can actually show those periods on the periodic table. We can show the period. So the period number are found to the left side of the periodic table. So if you can see right here, this is 1, this is 2, 3, all the way to 7. They represent all the period. Now we'll take it a step further and we'll talk about what those periods actually mean. So we can take those periods and we'll put them in an atom, or we'll put them in perspective. You realize that this blue spot here is the nucleus. And the first shell, right? The first shell immediately after the nucleus is given that number 1. So we call it the first shell, right? That's why it's given that number 1. But in quantum chemistry, we denote that as n. Okay, so we say energy level number 1, or principal quantum number 1. Okay, principal quantum number 1, or we say energy level 1. So all these periods that you see represent the number of shells. I've explained that in class a couple of times, and it's important for me to reiterate that fact, because when you have an element in period 4, that means that that element has its valence electron in energy level number 4. It means that that element has 4 energy levels. Again, the periods represent energy levels. So the highest number of energy levels that you will see occupied in an atom is going to be the 7th one. And that would be like in elements like francium, radium, that are all in period 7. Electronic configuration is a way to show the order in which the electrons are added to an atom using the periodic table. And we will show this, and we will show that this all ties to the quantum model. So after this unit, we're going to look at what the quantum model is. Again, we've already seen that before. Remember the electron cloud model? If you've forgotten, you can go back to your packet and you look at it. I think that was unit 3. You can go back and check on history of the atom. We looked at the quantum mechanical model or the electron cloud model. You look at that model of the atom, you will come to terms with what we're looking at right now. So the periodic table, maybe you've never noticed, the periodic table uh, is actually arranged in blocks, as you can see on this picture right here. The first two groups, you can actually break that out of the periodic table and it will give you a block. And so those first two groups are called the S block. Now, Those I was talking about called a transition metal. If you count them, there are actually 10 groups in that block. Starting from scandium all the way to zinc, there are actually 10 groups in that block, and it's called a D block. There are two groups in the S block. Now, if you come to the P block, starting from boron all the way to neon, there are 6 groups in this block. Now, down here you have the F block, which is the one below the transition metal. They're called the F block or the heavy transition metals. And in there you have 14 groups. If you count from here all the way here, right, you realize that they are 14. And again, I want you guys to pay attention to this number. How many groups do we have in the S block? How many do we have in the D? How many do we have in the P? How many do we have in the F? I want you to count that on your periodic table, and I want you to write that down because it is going to be useful, as you will see very soon. So if you could color, that would be fine. If you could take your periodic table, we have a lot of color pencils in front of the class. You can do that. You can color the blocks, right? It will help you. So if you look at the first two groups, in addition to helium, that's right there, you can color them yellow. They represent the S block or the S orbital. Okay. The P block, you could pen that green. You could pen the P block green. Okay. There are 3 types of P orbitals: the X, the Y, and the Z. But for the S, there's just one type. Okay. For the D, we have 5 different types of D orbitals. Again, these are numbers you need to pay attention again. Orbitals, what are orbitals? Orbitals are just specific regions around the atom where the probability of finding the electron is highest. So think of it as where you live in your house, your room, okay? So your room in this case will be just your orbital. That is a region in your home where the probability of finding you when you are home is highest, okay? At every point in time, the probability of finding you is highest. Just like your room number where you attend your classes as your orbitals. Because when you have a chemistry class, the probability of finding you is highest during that time because the probability that you will miss school is low. It's not that high, right? So at any specific time, if we come to school during chemistry, when you have chemistry and we go to your room, the probability of finding you in that room is going to be highest. Okay, so you can take note of those numbers. The S orbital, there's just one type of S orbital. Okay, the D, there are 5 different types of D orbitals. For the P, highlighted green, they are what? They are 3 different types of P orbitals. And the F, there are 7 different types of orbitals. Those numbers will begin to make sense very soon. So if you remember, we talked about the quantum mechanical model. In that model, this is what we had. Okay, this is what we had right there. You can go back and look. This is what we had. So these orbitals, right? You can see the S. We said the S is spherical in shape. Now let's look at their capacity now. The S orbital, it looks like a sphere. And now what is its capacity? The S orbital can only take 2 electrons. The S orbital can only take 2 electrons, right? This is why the first 2 groups on the periodic table are the S block. The first 2 groups are called the S block, and we will see why. So the S block show each period's number along with its electron. The S block has 1 orbital and that one orbital can only take 2 electrons in it. Have it at the back of your mind. An orbital can only take 2 electrons. Only. So when you label the first one, the first period, so what happens is those numbers that you see, right, they represent what? Energy levels or principal quantum numbers. As you can see, they all represent energy levels or principal quantum number. Okay, all of that. Now, the p block of the quantum model has three different type of orbital. So three different type of orbital give you how many electrons? Remember I told you that an orbital only takes 2 electrons. So if the p block has three different type of orbital, you just have to multiply that number by 2 because an orbital takes 2 electrons. And so the p block can hold a maximum of 6 electrons. Okay, 6 electrons. So in the p block, you can have up to 6 electrons. Okay, so now we are in the p, right? One thing you need to notice is that you don't have the p block does not touch, it doesn't touch period 1. So in period 1, if you go with period 1, if you have a ruler and you trace from hydrogen all the way to helium, you will realize that it does not touch the p block. The p block only starts from what? Period number 2. The p block only starts from period number 2. So there's no p block for period number 1. So if we are writing the electronic configuration of hydrogen and helium, we will not find the p block in that electronic configuration. Okay, so there's no p block in period number 1. So it begins in period 2 right there. Again, it takes 6 electrons. 1, 2, 3, 4, 5, 6. Okay, so we begin, those numbers will now begin to make sense. Remember I said there are 2 groups in the s block. The s block takes only 2 electrons. There are 6 groups in the p block. The p block only takes 6 electrons. And the same thing, you can begin to guess how many electrons are there in the d block, how many electrons are there in the f block. You just need to count how many groups they are in each block. Now, when listing the electronic configuration of an element, there are 3 things we need. We need the period number, we need the orbital letter. What are the orbitals that you've learned so far? We have the S, we have the P, we have the D, and we have the F, right? So 4 letters, S, P, D, F. Now you need the number of electrons that each orbital can take. Remember, the S can take 2, the P can take 6, the D can take up to 10 electrons, and the F can take all the way to 14 electrons. Okay? You always go in order, starting from period 1. You only write down the energy blocks you go through. Okay? We'll use the first method, but after that, we're going to use several methods to learn how to write this electronic configuration. What we're about to learn now is the first method. Okay, so if we want to write, for example, the electronic configuration of the element chlorine, the first thing we need to know is the position of chlorine on the periodic table. You can see right there, it is highlighted red. So what is the atomic number for chlorine? Chlorine is atomic number 17. Now, we will work through the periodic table until we meet chlorine. So we are going to go in order. Okay. So we said we needed 3 things. We needed the energy level number. So in order to go to chlorine, we need to pass through hydrogen, pass through helium, pass through lithium, beryllium, boron, carbon, nitrogen, oxygen, phosphorus, neon, come to sodium, magnesium, aluminum, silicon, phosphorus, sulfur, then we reach at chlorine. So that's the method we are going to use. So we go in order, we don't skip any element. Okay. So when you have this number one, when you have the number one, that's the first thing you want to write, right? You go through each block, and each time you go through a block, you need to write down the block you went through. So when you go starting from energy level number one, you have to write that one. This one here stands for period one. So you're going through energy level number one. And then by the time you touch hydrogen, what block is that? The yellow block. What block is that? It is the S block. Okay. It is the S block. Now, how many groups do you go through? You go through hydrogen and then you go through helium. That is two groups. How do we write it? We write it as a superscript. Okay, we write it as a superscript on top of that orbital. So we write it as 1s2. By the time we pass helium, we come right down here to lithium. Now, one thing you need to pay attention here is that with lithium is now a different energy level. So we need to write that different energy level right there. We need to write the 2 right there. And when we pass through lithium, we pass through beryllium, that's two groups right there. So we write the S block, and then we pass through 1, 2, and so we write it as 2s2. Okay. By the time we finish boron, we finish with beryllium, that same energy level is going to touch the P block now. We are now with the P block. So we write another 2. Whenever you change energy levels, you must rewrite the period number. Okay. So you write another 2. And in order to go to chlorine, I have to pass through boron, carbon, nitrogen, oxygen, fluorine, and neon. So that's 6. So I write 2p6. And then I'm done with that because the 6 cannot take more than, the P cannot take more than 6. So I write that. And then I come to the next one because now I'm done with period 2. I go to period 3 because my aim is to reach to chlorine. And now I'm now in a different energy level, so I need to write that energy level number. And so I have sodium, magnesium, that's 2. So I write 2s and then 2. Okay. And I'm done with that. Okay. But I'm still in the same energy level. So I need to rewrite that. 3. I'm now here with aluminum and I count. For my aluminum, I count how many steps before reaching chlorine. 1, 2, 3, 4, 5. So that's where I end. So I write 3p5. And so that is how I write the electronic configuration of chlorine using the SPD notation. So this is the electronic configuration using SPD notation. Again, it might look new, but you will get this, promise. Notice we only listed completed period and blocks and starting from period 1. Then the last period and block with the element we are looking for. Okay. So let's try oxygen. So again, we need to, if you try oxygen, this is what you're going to get. Okay. It's going to be 1s2, 2s2, 2p4. You need to try it yourself. Try phosphorus. Pause the video, try phosphorus. If you try phosphorus, you're going to get 1s2, 2s2, 2p6, 3s2, 3p3. One thing you need to notice here is that you are finding a home for the 15 electrons of phosphorus. So if you count these numbers at the top of each orbital, you will see they add up to 15. So 2 plus 2 plus 6 plus 2 plus 3, all of that add up to 15. So that's one way you know that you are doing it right. On energy level number 4, something happens differently. On energy level number 4, something happens differently with the D block. Energy level number 4, something happens differently with the D block. Okay. So I want you to draw this in your notes. Make sure you draw this. This is going to save your life. Okay. We use the first method to draw the electronic configuration. Now I'm going to introduce you to a second method. And so this is called a Christmas tree method, as you can see. We list all the orbitals and we are going to learn a different method to write the electronic configuration. So if you draw this, you pass arrows across like that. Okay? You pass arrows across. One thing you need to notice is that when you're writing the electronic configuration using this method, the orbital that this arrow is going to pierce through first is the one that you're going to write first. Okay, keeping track of the number of electrons. So what that means is that if I'm writing the electronic configuration, I'll always start with 1s1 with 1s. Okay, sorry, and then I go to 2s, and then I go to 2p 3s, because the arrow, when I pierce through this, right, this arrow touches the 2p before it touches the 3s. So I will fill the 2p with my guess electrons before I fill the 3s. And then this arrow, it pierces through the 3p before piercing the 4s, right? And so what is going to happen is that if I'm writing electronic configuration, I have to write a 3p before the 4s. Okay. So one thing you need to notice here is that the 3d, right, comes after the 4s when you look at this method. The 3d comes after the 4s, even though it is a higher energy level than the 3d, but something mysterious happens and the 4s actually fills before the 3d. Okay, you clearly see that with that method. So after the 3d fills, the 4p and the 5s follows, and so on and so forth. You just need to follow these arrows. One mistake you shouldn't do is that you shouldn't go like this. If you feel it in this direction, you get it wrong rapidly. Okay, you have to follow those arrows. So what happens is that when you deal with D block, right, there's this formula called the n minus 1. So by the time you reach on the D block here, remember, you remember that we were writing this number, right? We instead apply the n minus 1. So by the time you reach the D block, you take this, the n here is 4, minus 1 is 3. So the orbital number you're going to write is 3 by the time you reach here, instead of 4. And by the time you reach here, it's going to be n minus 1 again, which is 5 minus 1 is going to be 4d. Okay. So that's a 1s, 2s, 2p, 3s, 3p, 4s, 3d, not 4d. Okay. Then 4p, 5s, 4d, 5p. Because with the d, we apply the formula n minus 1. Okay. If you go to higher chemistry classes, you realize that here we apply the n minus 2. Okay. After 6s, the rules get a little strange, but I won't make you learn that far. You just need to know as far as 6s. Isn't there an easier way to write it without all the this 1s2, 2s2? Thinking about it. Why? Yes, there is. It involves using the noble gas since they are stable. So we can write the electronic configuration using a shortcut. It's and it's called a noble gas electronic configuration notation. So make sure you do examples using the other method. I will give you a worksheet. Make sure you complete that worksheet. Make sure by the time you reach at this point in the video, make sure you complete the worksheet before you use the noble gas electronic configuration. Let's say we want to write the electronic configuration of calcium. Reading the periods like we have been, what is the noble gas that just come before calcium? So usually, if you want to use a noble gas electronic configuration to write the electronic configuration of an element, you usually will use the noble gas that comes in the period before the period in which that element is. For example, calcium is in period 4. What is the noble gas in period 3? That's argon, right? So you are going to use argon as a shortcut to write the electronic configuration to calcium. If you were to use, if you were to write the electronic configuration of magnesium, magnesium is in period 3. What is the noble gas that comes in the period before magnesium? So that would be period 2. You come all the way here, that would be neon. Okay, so pay attention to that. So the noble gas that comes in the period before calcium is argon right here. Okay, so we know that argon is stable. Okay, we know that those noble gases are all stable, and so we can all assume that all the previous 1s, 2s stuff is included in argon, right? So what we do now is that we write that argon in square bracket. So, and that argon is what position on the periodic table? Position number 18. So we assume that when we write this square bracket for argon, right, it means that out of the 20 electrons that is in calcium, I have already added all the 18 in argon. So that's why it's a shortcut. It's much easier when you understand this method to write the electronic configuration. So when you write a square bracket, it means that all the 18 electrons, the first 18 electrons of calcium are already included in here. So the only thing that will be left would just for me to go after argon. I will just write the period number, which is 4 right here. And then for me to get to calcium, I go through 1, potassium, then calcium 2. So I'll write it as calcium will be argon 4s2. So that is a shortcut. So it only allows us a way not to write all those 1s that came before 1s, 2s, 2p, 3s, 3p, all of that is embedded into argon. So that's called the noble gas. When you write electronic configuration this way, we call it the noble gas electronic configuration. So you can try silicon. Okay. So again, for you to get to silicon, the noble gas that comes before silicon is neon. Okay, so you write that in square bracket. And so you assume that all the 10 electrons before silicon, or the 10 electrons out of the 14 for silicon, are already embedded into neon, like that. And so after neon, how do you get to silicon? You go through the 3s, okay? 3s2, because you go through sodium and magnesium, so that becomes 3s2. And after that, you touch the p, going through aluminum before getting to silicon, so 1, 2. So that's why you write 3p2. So writing it this way gives you the noble gas electronic configuration for silicon. Again, you can always pause the video and reflect. Okay, so let's try a harder one. You might need the Christmas tree for this. So we can take an element like zirconium. Okay, zirconium, you can find that right on the periodic table. And again, you will need a Christmas tree for this one. So was for zirconium, again, zirconium is in pure 5, and so you realize that the noble gas before zirconium, or in the period before zirconium, is krypton. So you write krypton in there, right? And after you write that, it means all the electrons before, or all the electrons up to krypton, right, are right inside. The right inside of this krypton. Now you are now left with only 4 electrons to fill. So you write 5s2, and by the time you touch the d, right, remember it's the n minus 1. So if it's period 5, right, you need to take apply the n minus 1 formula for the D block, which is going to be 5 minus 1, which is 4. So you write a 4D2. Okay, so that's the noble gas electronic configuration for zirconium. However, the correct way to write this is to put the numbers in order because the fourth energy level is closer to the nucleus than the fifth. So we can rearrange it that way. But I rather prefer the first one because if you write it this way, some people will get confused thinking that the D will fill before the 5s. As you can see, the 5s is full, right? Because the capacity of an S is only 2. And so when it has 2, we consider it full. The capacity of a D can go up to 10, but this one is there are only 2 in there. So it is not full. So I rather write it this way first. Even though this is a proper way, but for understanding, I want us to write it this way. I don't mind until you understand and you know what you're doing. So you can try antimony. You just need to locate that on the periodic table. Again, you will use scripting. And how do you get to antimony after that? You pass through the 5s, 2, and then by the time you get to the D, you apply the n minus 1 formula, it becomes 4D. And so you go through all the groups of the D, and so you write 4D10. And then after that, you enter into the P block, right? Again, by the time we reach the P block, we just write the period number. We don't apply the n minus 1 rule. So write 5P. And so you count 3 groups before you reach antimony. So that's why it becomes 5P3. So every rule has an exception. So we are going to look at the exception to the rule. Chromium is an example, and we're going to see. We will write electronic configuration of chromium normally, right? So if we were to follow what we just learned, this is going to be the electronic configuration of chromium. So this exception is called a Klikovsky rule, right? I'm not going to pay attention to that, but I just want to expose you to that name because if you do chemistry later, you might meet that again. It's called a Klikovsky rule. So this will have normally been the electronic configuration of chromium, right? But something strange happens in terms of the orbital trying to achieve stability, okay? So if you look at the D, what's the capacity of the D? The D can take all the way to 10 electrons. Okay. So when we feel electrons, usually the stability of the electron is when they are full. So when they are full, they are stable. For example, when you have a P6, the capacity of a P is 6 electron. If it reaches the 6 electron, we say it is stable. The capacity of the S is 2 electrons. When it reaches 2 electrons, we say it's stable. Now the D is not stable with 4 electrons, but the S is stable because it's full. Now, so again, when the orbital is full, it is stable. Now, if it cannot be full, the next thing that it wants to be is half full. So an orbital will prefer to be half full than incompletely full. So incompletely full here will mean that it is not full, neither is it half full. So when we talk of half full, we're talking about the capacity of the orbital. So if the orbital can take 10 electrons, half full will mean 5. Okay? So if an orbital can take 2 electrons, half full here will means half of 2, which is 1. So the D is incompletely filled, while the S here is full. So these electrons will rearrange in such a way that they achieve maximum stability. So what happens is the S will give 1 electron out of these 2 to the D. When it does that, notice what happens. It is going to make the D half full. It's going to make the D half full and the S half full. So orbitals will prefer to be half full than have a situation in which one is full and the other one is incompletely filled. Okay, so the right electronic configuration for chromium is by the time it reaches after the 3p6 is going to be 4s1 3d5. So chromium makes an exception. Another element that makes an exception in the periodic table that you easily see um, is manganese does that exception. No, I mean not manganese, copper. With copper, we have that same exception. Copper 29 electrons, right? So the normal electronic configuration, if we follow the rule, will have been this one. So notice here we have the D that is incompletely full, right? It is not stable. And so the 4s is stable because it's full. So this S will prefer to be half full and make the D full. So it will promote its one electron into the D such that it gives you 4s1, 3d10. Again, these are the exceptions to the rule. Okay, they are the exceptions. It doesn't mean that that's what you're going to do with all the elements. Chromium is a common exception you will meet. It's important for you to write that down so you remember. Copper is an exception to the rule, okay, whereby an electron is promoted or they rearrange themselves to make sure that they achieve the maximum stability. Remember that the maximum stability is achieved when both orbitals are full. If they cannot be full, what they will try to do is to have a situation in which one is full and the other one is half full. If they cannot have that one, they will rearrange in such a way that they will have half full, half full. It is when they cannot, or when there is no possible rearrangement that will lead to this order, that is when they just get what they get. Okay. So other exceptions are gold and molybdenum, but I'm pretty sure I will never give you an example on gold or molybdenum. These are higher elements that will follow the same Klikovsky exceptions. Okay. So at this point, I have come to the end. So I will expect you, right? I will expect you to make sure you fill your packet all the way to here.